and protons having a relative mass of 1 and neutrons having a mass of 1. Electrons are really light, 1 over 1836. The charge is +1 -1 0. Okay, so that is now we started talking about the structure of an atom. I told you that the nucleus has protons and neutrons, and the electrons are all attracted to the nucleus, which is the middle nucleus over here is positive. It's positively charged. Just hold on 1 second. My pen has stopped working. So you're just opening the board from another place. So anyways, I'll just continue. We were at this point that the nucleus is positively charged. The electrons are all attracted to it. The electrons, they reside in shells. The first shell has just 2 electrons. The second shell has 8 electrons. Third shell has 18 electrons. And you have the fourth shell, which has 32 electrons. And then you've got a fifth shell. So you can just figure out the number of electrons that are present in a shell by just using the formula 2n squared. So electrons are residing in shells. And then I told you about what's incorrect in the diagram that we draw. Whenever we draw a diagram of an atom, we show electrons as particles. The thing is, in reality, what happens is you're not able to actually see those electrons. It's very hard to actually figure out where those electrons are. What actually happens is electrons behave in this manner. That if you have a hydrogen atom, that's the simplest atom. What that means is that there's only one proton and one electron in a hydrogen atom. So the positively charged nucleus and the electron is attracted to it. But the electron is not a stationary particle. It's moving or whizzing very quickly. So I gave you an example of a swarm of bees around sweets. So I mean, there is no exact path of where the electron is. The electron has a very haphazard movement. It's trying to escape, but it's attracted to the positive proton, so it's not able to sort of move around. So imagine a bee that's whizzing everywhere, but it's not able to escape because it's attracted to the positive proton. So what happens is the electron is moving so fast that you can't really predict exactly at any specific time where that electron is. What you can do is you can demarcate a region around the nucleus, and you can state that the electron is somewhere in that region. So electrons, or the behavior of an electron, it's not shown by this spherical path. I mean, there is no path actually. A better representation of an electron is that you describe it with a region where you're able to find that electron. So electrons are going to be described by the region or area that they occupy around the nucleus. So that's known as a high electron or a high probability region. So if somebody says you that where's the electron, you can tell them that it's somewhere in this area. You're not sure because it's moving so quickly that to an outside observer, it appears that it's everywhere. I gave you the example of a fan. Like the blades of the fan, if they're moving, they sketch a circular path. In that circular path, you can't really be sure where the blades of the fan are. To an outside observer, if you see a fan that's moving very fast, it would appear to an outside observer that the blades of the fan are everywhere in that particular area. So anyways, so your electron is like it's going to be described by this region. This region is called an orbital. It's the high probability region around the nucleus. So every time from now on, electrons would be described by their orbitals. It's a specific place around the nucleus where there's a pretty high probability you'll be able to find the electron. So, and there are different types of orbitals. So this is another thing that we did, that different orbitals have, they've got different types. So you've got an s orbital. An s orbital is a spherical region around the nucleus. So if an electron resides in the s orbital, so that electron is whizzing in that particular area. It's somewhere in that area around the nucleus, sketching a spherical region around the nucleus, and you can say with a lot of certainty that the electron is somewhere in that area. So that's your high probability area. Similarly, you have another type of orbital which is dumbbell shaped, that's known as a p orbital. Now, in a p orbital, what happens is that the electron, if you're trying to find an electron and an electron is residing in a p orbital, the electron would be somewhere on either side of the nucleus. I mean, it's not going to be here, it's not going to be here, but it would be buzzing somewhere over here or somewhere on this side. To an outside observer, it would appear that the electron is everywhere in that area. I mean, it's moving so fast that the negative charge could be experienced everywhere in that particular area. So that's your p orbital. And I told you that the p orbital has directions. I mean, you can have different types of p orbitals. Directions are dependent on the axis. Like you're going to have a p orbital lying on the x-axis around the nucleus. That's the center, that's the nucleus. So the electron could be either on this side or this side. So I mean, it would be buzzing around. Think of it as a bee that's buzzing around on either on this side or this side. That's known as a px orbital. Then you have the electron could exist in the z orbital. The electron could be buzzing somewhere in this area, occupying these spaces. That is known as a pz orbital. And you've got an electron that could be buzzing in these spaces over here. That is known as a py orbital. So remember, p orbitals have directions, and you've got px, py, and pz orbitals. Together, this thing is referred to as a subshell. So the thing that you see over here, this thing over here is going to be referred to as a subshell. My main writing pad stopped working, so which is why I'm having trouble writing. As anyways, that's a p subshell, and I'm going to explain what a subshell is. A subshell is this subshell over here. It's a group of degenerate orbitals. So it's a group of, they use a word degenerate orbitals. I'm going to explain what. I mean, you already understand. Hopefully, you understand that. This thing. Hopefully, you do understand that it's a group of orbitals like px, py, and pz. If you combine all the regions together, this entire thing is known as a subshell. Degenerate. What the word degenerate means is, it means the same type. I mean, correctly, it's basically the same energy level, or you can say the same. We're going to come to energy levels later. Same energy level or type. So there is no difference between px, py. So there is no difference between px, py, and pz. They're all exactly the same. But if you group them together, that's known as a subshell. Is this point clear to everyone?
Yes, sir.
Okay, Aisha, Anna, Alicia, Ahmed, is this clear?
Yes, sir. Yes.
So that's your p orbital. Remember, the electron would exist on either side of the nucleus, and it's direction dependent. So there would be 3 types of p orbitals, and if you group all of the p orbitals together, that thing would be known as a subshell. So this entire thing would be known as a p subshell, and it's a group of degenerate orbitals. Now, number 3. The third one is, although it's not. I mean, the shape is not in your course. It comes in A2, So it's kind of in your course, but you don't have to study now. But since you are studying, so we should study this together. That's known as a d orbital. I mean, the knowledge of the d orbital is in your it's in your course, but the shape is not in your course. So that's your d orbital. What's a d orbital? That's a clover leaf shaped orbital or region. So it's a clover leaf shaped region. What happens is that the electron could exist in four lobes now. So if an electron is residing in the d orbital, it's a region around the nucleus, and that region. So that region would be the electron could exist in four lobes. It could either occupy these spaces or the spaces that are above and below. So the electron would be buzzing in these areas. The electron would hardly exist in these spaces over here, but it would be occupying these spaces. So just like a bee, it would be buzzing around in these spaces. So and it would be doing that so fast that to an outside observer, it would appear that the electron is existing in every location in that area. The probability of finding the electron over here would be minimum. Over here, so these spaces would be empty. You won't find any electrons over here. So that's a typical shape of a d orbital. Now the d orbital is also directional. It has many different directions, and we can just copy paste an image for a d orbital, so you can understand what the I mean, this one looks good. Just one second, copy image. So this one over here, if you can see this properly, this thing over here. So the electron exists. The center part is the nucleus. That's the nucleus. The electron density would be lying. Remember this three-dimensional space around the nucleus. So this clover leaf shaped orbital could be lying in the on the xy plane. That's known as a dxy orbital. So there are 5 types of d orbitals. So this one is, let me mark this clearly. So this one over here is a dxy orbital. Here, just one second. Let me use a. So that's a dxy orbital. Because the orbitals, the regions of the electron where the electron is supposed to be found, they're between the axes x and y. This one is known as a dxz orbital because it lies in the xz plane. The electron density lies or the probability or the place where you're able to find the electron, it is between the x and the z axis. This one is known as the dyz orbital. And then you have this one, which is known as the x square minus y square. Remember, these are just names. So that's known as the x square minus y square orbital. What that simply means is that the electron density is lying on the x-axis and the y-axis. So if you were to find an electron,
Sir,
yes,
do we have to remember these names?
I mean it's better if you do remember them. I mean the shapes are not important. I mean these shapes. You get the shapes for the p orbital. You get the shapes for the s orbital. Not for the d orbital. Not yet. In A2, you're going to get. You'll be asked about the shapes. But remember, most of the d orbital that's part of A2. So you're not probably going to get a direct question in your AS exam about d orbitals. The only knowledge that you should have about d orbitals is that there are 5 types of d orbitals, and together these 5 types of d orbitals, that's known as a d subshell. I mean, if you group them together, this entire thing is known as a d subshell.
Thank you.
So this entire thing is known as a d subshell. And then you have an f orbital as well, which there is an f orbital which has 8 lobes. So for the f, you pretty much don't need to know anything specific, because f orbitals, they appear in atoms that are really, really big. So I'll just quickly go through f. F orbitals are, there are seven f orbitals in total. So there's 7 f orbitals in total, and together they're going to be called an f subshell. If you group them together, you call them an f subshell. And the other thing about this is that that it has 8 lobes. Most of them have the 8 regions around the nucleus. I'll just quickly go through the shape of an f orbital, of a typical f orbital, and how does it look like. So these are, most of them have 8 lobes. Forget the first 3. There's 7 different types of f orbitals. Most of them have 8 lobes. But anyways, the shapes of the f orbitals are not required, not needed. Here's another example of the regions around the nucleus where the electron could exist if an electron is residing in an f orbital. So 7 different types of f orbitals, that's it. So what is more important is the s and the p orbitals. You must know the shapes of the s and the p orbitals. That is going to be specifically asked in your AS exam. For the d, you should know that there are 5 different types of d orbitals that constitute, or they comprise, the d subshell. If you put them together, that's a d subshell. But you don't need to know the shape right now. The shapes are going to come in your A2 exam. F, hardly ever, it's hardly ever mentioned. But just remember this, that there are 7 different types of f orbitals, and together that's called an f subshell. So you've got all these orbitals and you've got all these subshells, right? So there are all these regions where electrons could exist, and there are all types of regions shape-wise that they could occupy. They could occupy a spherical region. They could occupy the electron would be buzzing like a bee in a dumbbell-shaped region, in a clover-leaf-shaped region. It could exist in a spherical region. So there are all types of different orbitals. So we're going to group them together. And before doing that, let's also discuss that how many electrons can occupy a single orbital. You've got all types of orbitals. So each orbital, it can accommodate a maximum of 2 electrons. Maximum of 2 electrons. So it might be an empty space, it might have 1 electron in it, or the maximum number of electrons that it can accommodate, that's 2. So let's talk about an s orbital, or simultaneously we can talk about a p orbital as well. So an s orbital it is spherical. Let me just 1 second, let me rub this off. So let's say this is a sphere. So S orbital is spherical. So a maximum, this is the nucleus, the maximum number of electrons that could be buzzing in this area, that's going to be just 2. Okay, that's the maximum number of electrons that could occupy an S orbital. Similarly, you've got a p orbital. And the maximum number of electrons that could occupy a p orbital is that if they are in a p orbital, if they're occupying a double-shaped region around the nucleus, so maximum there would be 2 electrons, and those 2 electrons would be randomly just buzzing around in this space over here. They could be, because they're moving so fast and they're moving so haphazardly, that the electrons could be together in this part, they might be spread all over the place. So maximum 2 electrons. So each orbital can accommodate a maximum of 2 electrons. So all these orbitals that we talked about, all these orbitals, these d orbitals, each orbital. Remember this entire thing when it comes to d.
Sir, I have
Yes.
another question. You know, for the p orbitals, how there's 2 circles, do the 2 electrons just stay in that one circle, or do they move to both of them?
Okay, I mean that's my point. Like that's your p orbital, right? My point is, think of the electron as a bee, right? It's, I mean, the two bees that are just randomly haphazardly moving around. So they could be at any place at any moment. Do you get my point? The only thing you're sure of is that it's.
Yeah, thank you.
I said the only thing you can be sure of is that you can be sure of that the electrons are somewhere in that area, but you're not sure. I mean, so that's the whole point of orbitals. I mean, thinking of electrons as being occupying spaces in orbitals, the reason we're doing that is because it's very hard to actually locate exactly where the electron is. And it's moving so fast that to an outside observer, it would appear that the 2 electrons are everywhere in that space. Okay, so if something moves really fast, like a fan that's spinning, right? Okay, if we can find a good image of a fan that's spinning. So if you think of a fan that's spinning, maybe this one. So I mean, you can't really predict where the blades of the fan are. I mean, there's a spherical region, and you can be sure that the blades exist in that particular space, but you're not sure what is their exact position. Is this point clear?
Yeah, also, you see the pink region, the 2 circles, that's one orbital, right?
Yes, that's entire thing is one orbital.
Okay, thank you.
Okay, so don't think of it. I mean, there are 2 lobes, but this entire thing is one orbital. So if I say an electron is in a p orbital, that means the electron is everywhere in that space, or we're not sure where exactly it is, but it's somewhere in that space. So the same goes for the d subshell. Like if I say an electron is in the d subshell, then it might be in all of these lobes. We're not sure where it exactly is, but it might be present in somewhere. It would be buzzing around somewhere in either of these lobes. And the same goes for the f orbital. So each orbital can accommodate a maximum of 2 electrons. TK, is this clear? Amber, this is clear. France, is this clear? Mariam, is this clear? Any questions? Anna, Alicia?
Yes.
Achha. So now there's another question, which is, so we're only focusing on a single orbital. We're just focusing on one orbital, and I'm saying that each orbital can accommodate a maximum of 2 electrons. So all the orbitals that we studied, each one can accommodate a maximum of 2 electrons. Now there's another question, which is that if you have an electron, the electrons are negatively charged, so the electrons are going to repel each other. So it would be kind of really hard for the 2 electrons to actually exist in the same place or occupy the same orbital. Like, imagine the 2 bees that are repelling each other, and they're buzzing around in the same space around the nucleus. So kind of really difficult for them to actually exist in the same place. So electrons, they repel other electrons because they're both negatively charged. Okay, so they're going to both repel each other. So how do they stay occupied in the same space? Because it would be very hard for the 2 electrons to actually exist in the same place because of the repulsion that the 2 are going to have for each other. So there's another concept, and that's called, I mean, this thing is known as a spin pair repulsion. So there's another very tiny concept which could be confusing as well. So this is known as a spin pair repulsion. What that means is that every elementary particle, it has, it's got an electric field, right? An electron has a negatively charged electric field. So you've got an electron, you've got another electron. The point is, they're repelling each other. Why? Because their electric fields are repelling each other. So they've got these electric fields which are not going to allow them to stay together. So how does this repulsion, how can that be turned into a force of attraction? The way it's turned into a force of attraction is that, remember this, that all elementary particles, they don't just have an electric field. It's not just an electric field. They also have a magnetic field as well, which is why when you study in physics, you always talk about electromagnetism. It's because the electric field and the magnetic field are kind of linked together. You studied motors, right? I mean, there's electrons flowing. Why is there a magnetic field being produced? Why? Because every electron, now in chemistry before this, you haven't studied this, but every electron has a magnetic field. So what happens is that the electric field is repelling each other. The negative is going to repel the negative, but every electron is going to have a magnetic field. So if this electron has a particular type of magnetic field and there's a north pole on this side, and that electron has another magnetic field, and this side there's a south pole. So what are the magnetic fields doing? The magnetic fields are attracting each other. So your magnetic fields it attracts. So from now on, whenever you see an electron, don't think of it as just a negative charge. Don't think of it as just having an electric field. Like this is -1, this has a -1 charge. Remember, all elementary particles, they also have an accompanying magnetic field as well. So if negative charge repels negative charge, that means there's an electric field of repulsion. There's an electrostatic force of repulsion. But at the same time, if one of the electron has a magnetic field and that magnetic field is the north pole side, and the other electron has a magnetic field and the side facing that is a south pole, then the magnetic fields are going to attract. So the force of repulsion of the electric fields gets cancelled out by the force of attraction of the magnetic field. So electric fields repel, but the magnetic fields, they attract. So which is why the two electrons are going to stay in the same orbital. The force of repulsion will get cancelled out. Do you get this point?
Sir,
Yes.
you know how there's magnetic fields, and if we ever got a question about it, would they tell us which direction is the North Pole and which one is the South?
You don't need to know that. I mean, this is the only thing that you need to know. Just this. I mean, you're not going to be asked about the question. I mean, what is important is that the two magnetic fields must be opposite to each other. Like if this side is facing north, the other side must be the south side. Only then would the magnetic field attract, right? Because if this side is also the north pole side, then the two electrons would repel each other, and then there's going to be a magnetic force of repulsion as well. So for them to cancel out the force of repulsion, the magnetic fields must be opposite. Do you get my point?
Yep.
So apart from this, I mean, you just need to understand the concept. That's it. You wouldn't get a detailed question on this. What they'll just ask you about is, or they can ask you about is, how are the two electrons together? So you're just going to write that the electric fields. There's not electric field. There's an electrostatic force of repulsion. So negative repels I mean, that's the first point, which gets cancelled out by, because there's going to be a uh, magnetic attraction. There's going to be the two electrons are going to be attracting each other. The word or the term that they're going to use is that the electrons have opposite magnetic dipole moments. I mean, that's the technical. Instead of calling it a magnetic field, they call it, or they refer to it as a magnetic dipole. I mean, dipole means that they have a north pole and a south pole. And sometimes that's also known as that they have opposite spins. I mean, there's another way of saying that, and that is that the electrons have opposite spins. The word spin refers to the magnetic field. Okay, so just remember that they don't call it a magnetic field, they call it a magnetic dipole moment, or they call it a spin. They call it that they have opposite spins. Because most of the terminology is when, like in the 18th century, the understanding of an atom was all about spins, and so they keep using the same terms. They haven't changed the terms. Just remember that opposite spins means that they have opposite magnetic fields. So this is why the electrons, even though they're repelling each other, but that force of repulsion gets cancelled out and gets balanced out. So the two are kind of going to cancel each other out. Is this point clear to everyone?
Yes, sir.
Okay. And moving on from there, there's so they're going to have opposite spins. And the way electrons are going to be represented from now on is, a lot of times in certain diagrams, for example, they will tell you an s orbital. An s orbital would simply be represented by a box. So let's say that's your s orbital. So there's just a box, and that s orbital is going to have two arrows. One is going to be in the upward direction, the other one is going to be in the downward direction. That indicates the two electrons. Okay, so the electron is represented by an arrow. So you have an upward spin and you have a downward spin, which basically kind of just means that they have opposite magnetic fields. The first one is usually referred to as the upward spin. The next electron is, the s orbital is going to have two electrons. So by convention, one of the electron is referred to as the upward spin, the other one is referred to as the one having the downward spin, or the downward magnetic dipole moment. So always remember that whenever you have two electrons in an orbital, the two electrons are going to have opposing magnetic fields, which is why they're going to attract. One of them is the north pole, the other one is going to be the south pole. So that is why the two electrons are going to stick together in the orbital. They won't really go very far away from each other. The force of repulsion would get cancelled out. Why? Because they have opposite spins. And that's the way to represent an s orbital. I mean, you can draw the s orbital, or you can, there's a box representation. The same goes for the p orbital as well. You can just put a box, there's a p orbital. One electron is in the upward direction, the other one is in the downward direction. The arrows, they represent the magnetic dipole, which I can add over here. Okay, is this clear?
Yeah.
Okay, so that's just something that you should know of because of the representation. So always remember, you've got all these orbitals and you have electrons in them, and the electrons are going to have opposite spins. They can't have the same spin, because if they have the same magnetic field, even the magnetic field would repel. So that would be impossible for the electrons to exist in the same space. So is this clear so far? Everyone.
Yes.
Now the next thing is, you've got so many orbitals and so many subshells. Like the subshell is a group of orbitals, right? How do you figure out where the electron is? Is it, I mean, is it buzzing around in a spherical region? Is it buzzing around in a dumbbell-shaped region? Is it buzzing around in a clover-leafed shaped space, occupying a clover-leaf shape? So how do you figure this out? So I'm going to make, as the first thing is, I'm going to make a table of subshells. So the first one is an S subshell. Now the S subshell has only a single S orbital, that's it, nothing else. So it has a single, just one of them. The S orbital has no direction. Like you can turn, I mean, it's a sphere. You can't, even if you turn it around, it still looks like a sphere. The P orbital or the P subshell is actually made up of three P orbitals. One is Px, then you've got your Py, and then you've got your Pz orbital. As a pair, you've got your D subshell, which we drew earlier. I'm just writing the same thing down. So then you've got your D subshell. Your D subshell is made up of five orbitals. There's dxy, dxz, dyz, and then there is dx square minus y square. TK, we just did the shapes earlier, so that's dz square. And in rare cases, some atoms have an f orbital or f subshell. So just remember that there's 7 f orbitals. So how many, which subshell is going to have a total of how many electrons? Like the first one, every orbital can have a maximum of 2 electrons. So if you are referring to a subshell, if you're grouping them together in the form of a subshell, the first one can have a maximum of 2 electrons because it only has one orbital, and an orbital can have a maximum of 2 electrons. If you look at a p subshell, there could be a total of 2 electrons each in every one of the orbitals. So that means that there's a maximum number of electrons would be. So the maximum number of electrons that they can have, that would be 6. So a p subshell can have a maximum of 6 electrons. The d subshell can have 2 electrons in each of the orbitals. If they have 2 electrons in each of the orbital, the maximum number of electrons that they can have less than 10, but that's the maximum number of electrons. And the f orbital can have a maximum of 14 electrons. So I can show you the p orbital because the p subshell, because we drew it. I mean, this was the p subshell. So there's a p orbital px, there's a pz, and there's a py. So if you have 2 electrons buzzing in this area, and you've got 2 electrons that are buzzing in this area, you've got 2 electrons buzzing in this area. So if you group them together, so that's a total of 6 electrons. So is this point clear? Clear? Yes or no?
Yes.
So Tika, you've got your subshells. So how do we know where the electron is? Which region is it occupying? What is the shape of the space that it's occupying? That's a question. But before answering that question, we have to talk about shells. What exactly are shells? Now in O levels, you did study that you have different types of shells. I mean, there's shell number 1, shell number 2. I mean, they're numbered. So there's 1, there's 2, there's 3, and so on. The first shell is the one that's closest to the nucleus, right? In O levels, and they're also referred to by the alphabetical letters, which are K, L, M, I mean, you start off with the K shell, then L, M, N, and so on. So you've got all these shells. And the shell is also referred to as the principal quantum number. So that's referred to as the principal quantum number. Now, the shell is not a real thing. It's not a physical thing. What the shell indicates is that it simply implies energy level. So unlike O levels, it's not a real thing. It's not a physical thing. It's the energy level. Like if an electron is in the fifth shell, that means it's very energetic. If the electron is in the first shell, that means it doesn't have a lot of energy. So as the shell numbers grow, that simply means that the electron is becoming more and more energetic, or we can also refer to as the principal quantum number. If the principal quantum number is higher, that means the electron is more energetic. If the principal quantum number is low, that just means that it's less energetic. So always remember, the shell is not a physical thing. It's nothing. It just represents the energy of the electron. How energetic is the electron? So we'll discuss shells later in the next class then. Okay. Make sure you go over this once more. Okay. If you have any questions, you can ask me, and we'll continue tomorrow then. Okay. Is this all clear? Any questions?
Okay.
Sure, ठीक है. Okay, then let's continue tomorrow. Take care. Allah Hafiz.
Allah Hafiz.
Allah Hafiz. Allah Hafiz.